Good morning. Praise be the Lord and welcome to this, your last partial, guys. So, I'm recording this class because I don't know if this week we will have all the time of classes to conclude many things about the topic. And I'm explaining you here because there's a homework which will be related with this first week content. So, for this first week, my 11th graders, we have next object. We want to identify the family member of a function. So we will see then as many exercises because now we will study a continuation of algebra. I mean, a next level of algebra. It's essentially calculus, which is another branch of mathematics, what we will study. And with this, we're going to conclude finally this mathematics adventure. So for this first objective, I wanted you just conclude how to identify when a function is a linear or quadratic or cubic or absolute value or is the square root or a rational expression. All these will be useful at the moment to apply the rules and techniques we will study of calculus. And it's so important that you keep in mind those. Of course, many other skills that you want with the algebra passing those years, like solve equations, like factorize expressions, all these will be useful too. Other objective is I wanted we differentiate a function and the transformation that it suffered. Okay, it suffered some transformation. You will see how is that with some examples to prepare for you, and then that way we can conclude a pretty good idea of function. Okay? So it's pretty easy. And finally, talk about the domain, determining the domain and the range of the functions. When I talk about domain and range, I'm talking about the x and the y values that you normally graph. And if you don't remember something about it, the x values are called independent variables. Okay, the x is always the independent variables, and the y is the dependent variable. This is so important you keep it in mind. An independent mathematic means that can be any value if there's no restriction. And this is what we will see with each of these family function methods. So let's start with the family functions. Here we have the contents and we will study one by one the linear, the quadratic, the cubic, the square root, the absolute value, and the rational function. Of course, from each one, we will be concluding the domain and the range. Again, to have a clear idea about what's domain and what's range, just want to show you one example right now. Pretty simple. Look in one graph, for example, I don't know, I'm gonna try to make the graph of one polynomial expression. Suppose this graph moves like this, okay? Moves like this. And this graph right now doesn't look like have any restriction for the x values. I mean, there are no asymptotes in here. And if you don't remember, the thing of the asymptotes is normally or are normally the values that are related with the division of zero. Okay. So in rise, we will see some of these asymptotes. But right now, for example, what x values do you think are considering this if this continue extending and extending so more? So I'm trying to give you like the idea of what's that thing of domain and what's that thing of range. So right now we're talking about the domain. When you talk about the x values, you should talk about the domain. So I mean here is 1, 2, 3, 4, and many more values. Here is -1, -2, -3, -4, and many more values. What x values are included in the graph? If this continues, and this continues, it goes like opening, all the x values are included. So here you can conclude that the domain here, the domain of this function are all the real numbers. Okay, so that's the domain. It's pretty easy, the idea. It's like uh, you moving through this space. Okay, suppose that you are here and this is a wall. All that here, all that shape is a wall. If you find a way or any space to pass to the other side of the wall, not happening of course, to pass the other side of that wall, then you found a gap or a space in that domain, which is possible. I'm gonna show you another example too. Okay, let's talk about the range. Range is something similar of the domain, just that instead of concentrate in the values of now you're gonna do it in the values. of y. So what y values are included here? 1, 2, 3, and this go and go and go and go. -1, -2, -3, and this continue. Of course, this goes down and this goes up. If you see all those values again, the y values are included. Um, what about 4? Yeah, 4 will have a value here. What about 100? Yeah, if this continue opening upward, this 100 will have or will be a part of this. If you want to see it like the idea of pass to the other side of the wall, same idea. For example, if you are here and you want to pass to the other side of that wall, is that possible? In this case, not. Probably you can go around this space, but then there is not going to be one place to pass to the other side. And this is the idea. If there's not a place to pass to the other side, there's no any gap. There's no any problem. So then you can conclude that the range are the real numbers. Okay, we will see it with each of these graphs, each of these members of the family function. And essentially, this is what I wanted we conclude. Okay, this is so important to consider in calculus, specifically for the first topic we will study, which is the limits related with the calculus, right? This still being algebra. So here we have the family of functions, and probably I will concentrate just in those members, in the polynomial functions and non-polynomial functions. Of course, in non-polynomial functions there are more, inclusively in polynomial functions there are more. Okay, here talking about this one, but I will concentrate just in these three, okay, because the basic ones, and with this one, then I think we can understand pretty good what happened with the next, which will be the quadratic function or theta function, because have degree 4, or in general in polynomial function. Of course, here I'm gonna consider like more basic or use functions we already know. In this case, the absolute value function, the square root function, and the rational algebraic expressions function, or the reciprocal functions, like some books call it. Okay, so we will concentrate each of these ones, and we're gonna start with this polynomial function. Okay, then we will concentrate the non-polynomial functions. So you will see that this topic is pretty easy, just require that you identify when or what are the elements to consider the function like a linear function. To the same for the quadratic, what elements you need to consider to conclude a quadratic function, and so on. Okay, the same with the rest. You will see that's pretty easy, doesn't require a lot of procedure, just more analysis. So this is like more a theory part of the mathematics we will study. So let's start with the polynomial functions, in this case, the linear functions, then the quadratic, and finally the cubic. So let's start with the linear function. As you can see here, it is the linear function. So how is a linear function? Normally, the behavior of this function, it's like this: f of x, this f, and the x in parentheses is written like f of x, and it means a function in terms of x. Probably in some books you see it like y equals. The book we are using is like that. So the linear function we know is a simple one, is just like that. So y f of x equals x, or y equals x, it's the same. Okay, it's the same idea. We're gonna get used to use this f of x, the one that we will use in the classes. Okay, so what are the characteristics of a linear function? First of all, it has a variable x that probably will be with a number, probably will be with a number added or something extra, but the curious thing here is that the x has exponent 1. Okay, there is a simple case in here for the linear function, and there is one simple special case that's called a constant function, which at the end is part of this linear function. Okay, so I will add it over here, and that way I think probably you will understand better the idea of the domain in the range too. So I'm going to talk about the constant function, and the constant function is practically a function that works with a number. A is a real number. Yeah, don't think that A is A. No, A is a real number, and it's so important that, okay, so this constant function will be part of this. Let's conclude about the linear function. The curious thing about the linear function, first of all, the graph of this one, it's a line. Of course, this is not the display of that f of x equals x. This is another function that I have here. We'll show you how is that. I mean, the function that I have is x plus 2, but I can change that and just leave it like x. And as you can see, there he is. This is the linear function, f of x equals x. We will concentrate on this one because then the other functions, I mean, the transformation it can suffer is just move this line around. Like it's like have something like this. Can I show you with one little example? If you have it in blue like this one, some transformation that this can suffer is that you can move it all around these spaces, okay? So it's so curious, this linear function. Of course, if it's a line that goes like this, you can change the direction of this one. You can make it like like this, okay, go in another direction, but still in a line. That's the observation, and that's what we will study with the other functions, okay? So important characteristic of the linear function again is related with this. It has a variable x, and that variable x has exponent one. Normally the exponent one is not shown, okay, so it's not over there, but this is the idea, okay? So when you work with expressions like this, think in a linear function. What about next example? F of x equals to 5x minus 3. Is that a linear function? Of course, because half the x and the x half the exponent 1. Simple like that. What happens if you have f of x equals to, I don't know, 2x squared minus 5x minus 3, for example? It's something similar, yeah, but now you have this other part here that works with 1x that has second power, and this breaks apart the idea of linear function. So this is not a linear function. Okay, we will see what type of function is that one, and that's why I need that you be clear with this family of function numbers. Okay, I'm gonna classify the domain in the range. If you see here, I have the graph of a linear function, so I'm gonna make the drawing of one student who's gonna try to pass a wall to see what happens. So here we have the domain in range. Let's start with domain, and then we go with the range. So to consider the domain, we will see if you can pass this like working like a wall. What happened? Okay, there he is. Sorry. It's working like a wall, and if you see you cannot pass, there's no any place for you to pass to the other side. Okay, there's no way that you can. Don't say that you can jump to the other side. No, it's not like that. There's no way. So this is working like a boundary line. Essentially, what you want to know is passing through all the x values you have in here. Okay, all the x values which are in the x-axis, these ones, you will see a gap and a space that let you pass to the other side. In this case, you can go up, but there's not gonna be a space. So what happens when there's not a space? This is something that we can conclude pretty easy, and we can say because there's no space to pass to the other side, there's no any problem with the domain. That domain are all real numbers. What does it mean? It means that I can, and you can see it here in the graph, I can go and check, look and check more and more deeper what's happening in this expression. I'm gonna make this pretty tiny, okay? Better like that. And if you see, if I go to 486 negative, I still having a value here that correspond to this one. Can make this shorter. Yes, for example, in 4,000 negative 4,700, if you see still being a value that correspond to that one. So essentially, the domain is, when I talk about domain, I'm talking about the x values that are included in here. Is possible to not include some x values? Yeah, but in the linear function, it's not the case. In linear function, all those x values are of the graph, okay? So that's why the domain are real numbers. Something similar can happen with the range. Again, If you concentrate and look for a gap and a space that let you pass to the other side, consider this like a wall. And if you see now it's a long wall, okay, because I'm making those values, there's no one space, there's no a gap that let you pass over there. Okay, so there's no any problem. So if you see this idea of the domain in the range is related with this simple comparison of one wall, and if there's one gap that let you pass to the other side of the how can I say of the graph, okay, then this will be a space that's not part of the domain or the range. But in this case, all the y values are part of the range. Okay, if you see, for example, here I'm working with negative 1,880. Yes, cannot see too much good. And here is it have some values. Okay, you have a y value here that represents this value of the y-axis over there. Okay, we will see that in the constant function is not the same. Just let me show you why. A constant function is a type of linear function. Just that the graph of this one's pretty easy. And normally, for example, I'm gonna graph one basic one. The graph, what about the graph of f of x equals 3 equals 3? F of x equals 3 will be a horizontal line that passes through 3. So it's a line. That's the point. That's why it's a linear function. That's why we're still talking about the same. So it's a linear function that passes through 3. And of course, this is a coordinate plane. So this extends till the infinite. This extends till the infinite. The same for this one, because our lines. The same for this other one. And of course, for the line we graph f of x equals 3. So of course, if here you have f of x equals negative 3, then you're going to have a horizontal line passes through negative 3. We're going to do exactly the same idea to get the domain in the range. And I think now you're going to be clear about what's domain in range. If not, with next function, you will have a better idea about what it is. Again, the domain practically are all the x values you have in the graph, and the range are practically all the y values that you have here in the graph. So you will see what's the difference. Look, this one has a big inclination. This one doesn't have any. This will help us, I think, in a few minutes. And practically, we can use the idea of the man, okay, who we will see if he can pass to the other side or not. And if you see, um, talking about the domain, I mean, if I want to pass to make this guy pass to the other side of this wall, is that possible? Right now, no. I mean, there's no gap, there's no any space that will let him pass. So in this case, when we talk about the domain, we're talking about all those real numbers. I mean, I'm talking about one, -1, sorry, -2, and -3, and so on. And of course, the numbers between those two fractions. Everything it's included in here. That's why all real numbers are part of this. But now what happens if I want to pass to the other side? I can freely do it. Okay, I can freely do it. Suppose that I'm here. Okay, suppose that I'm here in this part. I can freely pass to the other side. There's not only one point. I mean, what y values are included in the graph? If you think that all the y values are included in the one, tell me what y value corresponds to one in this graph. Is there something related with the positive one in here, inclusively with the two? Inclusively with the 4. If you see, I jumped the 3 because it's the only one that has one value related here. I mean, all of them. And essentially, that's because the graph behaves like this. So here comes the curious part. What's the range? The range includes just one number in this case. The range includes just the 3 because it's the only y value. Remember, the range is related with the y values. Is the only y value that's included in here. How do I know that? Okay, first of all, I tell you something about inclination. This is how the line and doesn't have any inclination. Okay, that's why it stays like this. It's horizontal, and with a little bit of inclination, then I will include many more values like we have it here, right? With this inclination, the other So this is something important you keep in mind because for the topic we will study, which is related with calculus, that's called limits, we will see that this domain and range will be useful specifically where have sense to look for a limit. We will see that later. Okay, let me copy that guy, and I think we're gonna move with this one to our next function. So I think you're having right now like a good idea of what is domain range. With the next graph, which is the quadratic function, you will have now a clear and good idea about this word. Okay, so let's concentrate on this one. We will see same ideas for domain and range using that tiny guy, that green guy. It's an alien, I think, whatever it is. Okay, so suppose now the quadratic function. Okay, we will study. Sorry, the quadratic function. What does it have? It has something here. The quadratic function works with a variable x, but not to the power of one. No, we saw it in the linear function. Now it works with the second power. Every time is like this. If you see this second power expression like the greatest expression with x, then you're talking about the quadratic function, which graph is it's a parabola. So don't say you don't know it. It's something that you already studied in other years. So every time you see x to the second power, yeah, I know then you can have a 2 here plus x minus 3, for example. Yeah, you have exercises like this one, but the important thing is that you have this x to the second power like the greatest one. That's like the main characteristic of every quadratic function, okay? Pretty simple. Okay, let's use this guy to understand the idea of the domain range in this function. And probably, I don't know, I wanted to try to do something with it. Okay, in the domain, I'm gonna make this tinier. You will see big values over there. If you see the graph becomes to be stretched, yeah, but it's still being open and open and open. As you can see, still been opening a lot. And this is the curious part. It's still been opening more. Okay, so just gonna try to leave it over there. What happens if I make this tinier? Sorry, I zoom it. Of course, I will see better the opening, right? But my idea is this opens and opens and opens, and because it opens and opens and opens, if we ask to our little guy to pass to the other side to be like inside of that U, it's impossible. There's no gonna be any gap. There's not gonna be any space. So because of that, there's no space. The domain are the real numbers. Okay. When I'm saying this is if he can pass in that direction. Okay, the direction of the x values. Yeah, the x values makes this direction, right? If you see, if it's not clear what I'm saying x. For example, these two is related with that 4, okay, over here. These 4 is related with a 16 over there. So if you see, the way that the x values work is like this, okay, moving up or down, looking for one point that corresponds to them, or probably like we have it over here on the same x-axis, okay? So all those x values are included. You see, yes, all of them have a value because that's continue opening more and more and more. They still have values. And this is the curious part. Okay, this is the curious part. The main is real numbers, but now we go with the range. For the range, if you see those values moves like horizontally, okay, not like lines, of course. For example, 6 has a value here, and 6 has another value here, but 6 is included. 8 is included. So the idea here is consider this just like one half of this one like a wall. You will see why. So let's see what happened with the guy. It's possible that this guy passes through the other side. If you're thinking that no, it's because you're looking just those values that goes from 0 and up. Okay? There's no way, of course, that this passes through the other side if we have this 0 over there. Okay? Wow. So here we are. Here's the alien cannot pass. Yeah, because he's moving upward. But what happened if he tried to move downward? If he moves like from here, wow, this guy disappeared a lot. What happened if he passes through there? The kid does. Can he pass to the other side? Yes, he can really do it. So what happened here? There is a big gap. Of course, there is a big gap. There's a big space. If you see, there's no function. There's nothing here below. I mean, from the values of zero to the negative values we have that are infinite negative values, there are no any graph. There's no any graph. Essentially, this is the idea of domain and range. Where the graph is, in what x values are included in that graph, what y values are included in that graph. So what y values are included right now? If you see, the ones that are not included are like the negative values, -1, -2, -3, the numbers between those numbers, and of course until negative infinite. So where is where it is? It is in 0, in 1, in 2, in 3, and 4, and so on. Okay, so it goes from 0 to infinite. How can you represent that mathematically? Pretty easy. Okay, from 0, including the 0, that's why I have like a closed bracket, until positive infinite. Okay, and this is open. This is a notation. That's an interval notation. It's a topic that I think you study in 8th grade. It's about the number line. How can you represent numbers on a number line? Okay, so it's pretty easy to understand. I mean. So what about next one? What about next one? Let's concentrate on the next one, and I think we're gonna clone our alien we have over here, just to see if we can make him tinier. No. Oh, it's like dancing. So no, there he is. We're gonna stop over there, and we will see what happened this example. Okay. So we will see if this guy can pass like from here down to the other side to here to be like inside of this. I think that's impossible. There's no gap. And of course, you're going to say, yeah, he can pass through here. And then, well, no, come on. This line, this arrow means that this expand, continue opening and going more and more and more and more. Of course, mathematically, this is the idea of the infinite. And there's no way that he can pass like walking from below upstairs. Or if you want to see it like this, suppose that he's like enclosed. Can he go outside from this like jail? No, right? There's no way. So what happened with the real number, with the domain? The domains are in the real numbers. Okay. So pretty easy the idea of domain and range. So domain, real number, and that's something common that happened in this exercise. This is like a generalization. Okay, it's too common that in the cases of the quadratic formula, the domain be the real number. Like in here, the linear function. That's in the case of the constant function. The domain real numbers, the range real numbers. Okay, here something like that. The domain real numbers, but the range not always can be the real numbers in a linear function, specifically for the case of the constant function. So let's see here something different happens. Something different happens in this exercise. First of all, same shape, yes, same shape. That's something else. They follow the same shape, just probably it's tinier. It's a little bit wider. It's not in the same position like right now. If you see this one's like 0, 0, and believe me, here it is, like 0, 0, and that one's on like another position, right? So if we go and use the alien to see what happened and have it here and seeing if he can pass to this side, he can do it pretty quickly. I mean, he just move back a little bit, move down a little bit, then walks, and he is in the other side. So pretty easy, right? There is something interesting about this point. It's the vertex. I think I'm not gonna explain you that. The topic right now. So what will be the range here? From where to where? We have the values from, if you see, the range always related with the y value. So you're going to concentrate in all include those values in here. So what values are not part of the function? If you see these ones, like going from this -1, but not specifically -1, and down there. So essentially, the range in this case starts in -1, if you see, and then goes up. Why it goes up? Because the graph goes up, so the values goes with the range. As you can see, those this is like the correspondence they have. Of course, they have a correspondence the other side too. But the idea is what y values are in this graph from -1, like we have it over here, from -1 until, how can you write that? Pretty easy. From -1, including the -1, until the infinite. Probably your question is what happened if this opens onward? Okay, it will be something similar like this. Probably we will see some exercises, okay? But right now it's just that you have cleared the idea of how that works. Okay, let's copy that alien. And now let's see another function. So I think you have been getting clear the ideas of when is quadratic, when is linear, because the homework will be related with this. Now let's talk about the cubic. Let me, here it is. The cubic function is a little bit like the linear function, a little bit, okay? So cubic function behaves like f of x, f of x equals 2, x back to the power of 3. So differently than this x, the other exercise, now the exponent is 3, the greatest one, okay? You can have expressions like x to the power of 3 plus x to the second power minus 5x plus 3, for example, and you probably will say, okay, it's a quadratic. No, the greatest is the power of 3 expression we have over there, and this is practically what let us uh, think in the cubic function. We will see what are the characteristics for the domain, talking about the domain in the range. Okay, we will see that. I think it's pretty easy to identify what's the domain and what's the range of this expression. Okay, so if here we have this guy and we talk about the domain, if we have it here and we want to pass, we want that he pass like to the other side, cannot do it. There's not gonna be an space. Here this graph doesn't show us that this goes and goes and goes more. I mean, this goes down and this goes upward, but at the same time, it's like making an opening. I mean, still being like making and being this doing this like space wider. If you see, it looks like a parabola that cut it in half and the other half like upside down. Yeah, it's something like this. So here we can conclude that the domain of this cubic function are all the real numbers. Okay. Why? Because all the x values you have here are included. I mean, there's not gonna be a way that this guy can pass to the other side because all the x values are included. Let's see if the same happens, but now with the y values, okay? With the y values, you want to pass from here to there, but doing it in that way, horizontally. With the x values, he wants to do it like vertically, and with the y values, horizontally, okay? So can he pass through any space? No, right? There's not gonna be a chance. There's not gonna be like one space. Probably you would say, yeah, but here the graph ends. No, continue until the infinite. So he will not pass. There's not gonna be a space that let him pass. I will create one weird exercise. You will see that this is possible. I mean, in the limits topic, but to be honest, we will not be like more deeper than what I will teach you. Okay, because of the situation. Normally, I'm going more deeper, but I will give you the tools. I promise that. But I will give you the tools to understand the topic at home. Okay? This thing of the main range right now is like the base of this topic. So it's pretty easy to identify it. Okay, so I'm not gonna say more. I think you're clear with how the main and range works. But not always is real numbers. But we have it over here again. Just to conclude the idea of the domain and the range, if this value that right now we have is -1, has a value in the, sorry, not -1, that's -2, that's -1. That's a value in the graph, so it's part of the range. Of course, between 0 and 1, if you see, there are many more values. There are infinite values, of course. There are infinite values that are included in here that has a representation in the graph. What about the values between 0 and 1? All of them are included, if you see. All of them have like part of the graph. When something like that does not happen, okay, when you have something like a gap and a space, okay, it is possible. We will see when the exercise create the need of have one space with this example that I showed you. Let's continue because I think right now what we did is just finish with with the first part, okay, with the polynomial functions. Okay, so I think that we already studied the linear function, the quadratic function, the cubic function. So we already studied the polynomial functions. We will see. We will not see some more. Okay, we will not see more. Now we're going to concentrate non-polynomial functions. So what are non-polynomial functions? Expressions that are not polynomials, obviously, like the absolute value function, like the square root functions, like the rise function here, of course. Then I will add two more, or which are the exponential functions and the logarithmical functions too. But we will not see them like the main in the range because this is not going to be interesting from those. It's more interesting here to keep in mind what's the idea of mean and range. So let's start with those known polynomial functions and see what happens. So here's the absolute value function. Absolute value function is next one. F of x equals 2. And if you see those bars, this is the characteristic. If you see those bars, which are absolute value bars, you're talking about this absolute value function. The thing I was telling you, some books represent this y equals x pretty good with this idea. Here's the alien because he will help us to see what's the domain in the range of those expressions. And let's make that. So we're gonna concentrate those domain and range. Okay. So what x values are included in here if this opens and opens more? Not just to the left, to the right too. So if you think in all real numbers, you're totally right. Okay, so the real numbers are all the values included in here. What about the y values? If you see here, this 1, this 2, and the values between 1 and 2, for example, are included. That 0 is included. The values between 0 and 1 are included too, but some values are not included here. And that's why here we can use the idea of the alien to understand better the exercise. So if you see here, if we want to see what x values are included, we can see that he cannot pass. Sorry, he cannot pass through any of those values. Through -4, no, he cannot pass. Of course, through +100, no, he will not pass because here will be like part of the graph. But what happens if we want to do it through the y values? Can he pass? I think so. Okay, I think so because if he's here and he wants to pass like to the other side of the y-axis, essentially that's what we want, pass to the other side of the y-axis. Okay. So can we do it? Yes. Like from here, from this space we have it here. Why we have in spaces here we don't have graph? Okay, so the graph, this graph behaves a lot like the parabola, if you remember. Okay, the parabola doesn't have elements in the negative part. Okay, so the same happens here. So what's the range? The range are the values that starts from 0 and goes until positive. Okay, so that's the range, pretty easy. So the idea of the absolute value graph is that practically creates a symmetry like the graph of the quadratic function. It's the same idea, practically it's the same idea. Okay, so here you have the absolute value, which is the important characteristic here. Probably in some books they represent these expressions like this, for example, which is okay. This still being an absolute value function because you have this. Something interesting happens too, and they start to make functions, something like this, but this still being an absolute value function. So this is the idea. If you see those absolute value bars, no matter what's inside, um, can be any other expression, any polynomial expression here, and you're still talking about this absolute value function. So that's the curious part of this absolute value function. Of course, the domain in the range behaves like the domain of the range of the quadratic function. So let's see now another function, and in this case we have the square root. I mentioned this square root because it's possible to study in general the cubic root or the, the even index roots and the odd index roots. Even are the numbers like 2, 4, 6, 8, 10, or these ones, the ones that have exactly half. And the odd numbers are like 3, 5, 7, 9. Okay, those are the odd numbers. Of course, we will not concentrate on all those cases. We'll just kind of concentrate on the square root. Okay, because of the time, because it's pretty easy to see. And you will see here that something different happens than what normally happens in these other exercises. And you will see it that the domain in the range. Okay, so let's concentrate over there and let's talk about it. So I think you're clear with what's on a square root. What's on a square root? And if the square root is there, obviously you're talking about a square root function. It can be here x plus 3, yeah, but square root is there. And probably you're saying, yeah, but the x is to the power of 1. No, no. If you don't remember, this topic of square root is related with exponents that behaves like fractions. So at the end, the square root of x is the same as square root of 1/2. Okay, that's something that we study, I think, 10th grade, or you study 10th grade, and it's about the exponent. So, okay. So here we have the exercise. Whoa, there you go. The guy that will help us. And let's see what happens. So let's see what values we have in the domain. The idea is that if he can pass to the other side, I mean, he's here, but he looked for the way to pass to this side. He's totally um, he's totally smart first, and he's totally and something else happened in the domain, not like in the other exercises. So if you see, if he tried to pass through these positive numbers, it's impossible to pass. Okay, I mean, and he stays in zero, cannot pass, but he goes through the negative numbers. If you see, he have the chance to pass because there's a wall. He can freely pass to the other side of this wall and go free. So what's the situation here differently than the other exercises? The square roots working for real numbers cannot take negative values. If don't believe me, right over there, before, which will be 2, and try now the square root of -4, which will be a math error. And it's not a math error, essentially, is that you're not working with real numbers. Okay? Is that you will work here with imaginary numbers, but this is not the case. So what is the domain? What x values are included in here? Differently than this one, which we said are all the real numbers, here we cannot say it because all that negative part cannot be part of this, not included, okay? It's not included. So we have to say that the domain goes from this 0 to the right of 0 because all those values are included in here. Look, all they have a value that represents the 1, the 2, the 3, the 4, the numbers between them here in the graph. Okay, so the domain is, or R, sorry, R, the numbers from 0 to positive infinite. And something like this will happens. Something like this will happens with the range, okay? Now for the range, we will concentrate in the y values. So what y values are included here? So if you see this goes opens and opens and opens and opens more, so it means that if this guy passes through these positive values to like the other side to here, he will not have chance. I mean, if he try in 4, probably here, he will find like there's a wall that not let him pass. Okay, the same if he goes with 100 or something like that. Okay, but come on, I think you already see that there's a big space in here. And normally that happen because the square root gives you two answers. If you don't believe me, it gives you one positive, one negative, but it's too much common to work just with the positive. And here, because we're talking about functions, we consider this like the principal answer, okay? Just the positive one. And that's why here, this guy, if this guy try now to pass horizontally through the negative y values, he can freely pass. So what does it mean? He's in the other side now, look. So what does it mean? It means that that domain, sorry, not the domain, sorry, the range behaves like the domain we have right now. So what what y values do we have in here? If you see, we have 0, we have 1, of course, all the values between 0 and 1. We have 2 in the graph. Yeah, here we have 2 in the graph, and all the values between 1 and 2. Of course, this continue opens more, okay, and we're gonna have 3 and so on. So what values are included? From 0, because 0 is here, is included, until positive infinite. They behave pretty similar, okay? What happens if we have like another example? I'm gonna do another graph. That way you're gonna have like what I'm trying to say. Here is the y-axis, here is the x-axis, and I'm gonna make my own graph of this expression. Okay, I'm gonna do it in green. Okay, make it a little bit interesting. What about if we have the graph? The graph will be always behaving like this. This is something interesting. All the graphs behave the same, just that probably goes that way, goes another direction, goes in a different position. This is the thing. I mean, the shape will be the same, just that change. For example, what happened now with the guy? Can he pass through? Talking about talking about these values we have in here, the x values. Talking about the domain of the green graph. Can he pass through -2? No. Through -1? No. Through 0? No. Through 1? No. Through 2? No. Through 3, 4, 5? No. There's no way he can pass. The only way he can pass is from the values that are to the left of -2. In this case, -2.1, for example. Yeah, he can pass and goes. Okay? So something different happens here, and look what happened with the domain of this exercise. So what will be the domain of this green graph we have over there? It's something different. The domain here will be all those values that starts in -2, starts in -2, and then go and go and go and continue and continue and continue until the infinite. So from -2 to positive infinite. And probably your question is why I'm writing this like in this direction and not like that. Okay, because this is like in an opposite direction, meaning that it's open. And that thing that's open means that there's another value next to it. Okay, there's another value next to it, or that's not concluding there. It's not concluding there. Of course, infinite is not a number. Infinite is a tendency. I mean, if you're thinking the biggest number you know or you ever seen, I don't know, probably the amount of likes you have in one picture. There's another number bigger than this one. Okay, what happened if I add this a 1? Of course, the number that becomes now is bigger than 9,999,998. Of course, we're not gonna talk about those big numbers. We don't care about it. We want to see what's the behavior of these graphs. And what about the range? What about the range? Didn't say anything about the range. The range now, from what y value we start? We are starting from 1, and then this go up and up and up. So the range will be from 1 till positive infinite. And again, always when you talk about the infinite, will be open. Why here is closed? Why here that one's closed like this? Why is not like that? Open. Like this, okay? It's possible to have exercises like that. This is a math notation, something I think that you study in 8th grade, I don't know. And it's open if the graph have like this gap, like this space. This happens in something that we call piecewise functions, which practically is like combine pieces of other functions to conclude a new one. It's possible, and sometimes it's useful to model a real situation. Let's move with this guy to our next, and I think last function we will study. Of course, then I will have an exercise that will tell you, that will be prepared, that will prepare yourself to solve the homework. So here we go with the right function, and this I think we will finish. This one have something interesting. To be honest, those are the ones that we will start studying with the limit topics. You will see, and here I will remember that you remember how to simplify. I think that you should remember or study how to simplify rise. That's when you factorize the expression and look then if you can cancel. So how is a right function? Are functions that have variable on the denominator. The variable here can be to the second power, to the power of 3, can be to any power, it doesn't matter, but the point is in the denominator. You can have variables in the top, but if you have variables in the bottom, there are some many restrictions, specifically for the case of domain and range. Here we will see that this graph is the one that suffers more changes, where it concentrates in domain and in range. So it's pretty easy. I think we're gonna do like a general point of view of all the graphs, and in conclusion, we will see what are the elements that we have to consider at the moment to have those graphs. Okay. So let's see what happened with this guy. Let's see what happened with this guy. This guy here can move freely however he wants because there is an space. And if you see, that space is not make it in -1, is not make it in I don't know, -0.5, is not make it in 0.5 or in 1 or in 1.5 or in 2 or in 3. No, it's not make it there. It's in 0. This space 0 let him pass however he wants and go wherever he wants. So this 0 is a space, it's like a gap that I was asking you to identify, that let him pass in however position. So this x equals 0, I mean this value of x0, it's an asymptote. It's something that the graph will never touch it, and it have many sense. I mean, if you pay attention to details, you have x on the denominator. What happens if you have x equals 0? Then you're going to have 1 over 0, which is undefined. Don't think that is 0. Don't think that is 1. I'm sorry. Divide by 0 is impossible in math. And there are some ways to answer this. Honestly, the calculus let you find the answer of this by one way. Okay, we will see. But at the end, probably the answer will be not something that you like. Okay, I don't know. So what's the domain? If you see all the values are included, okay, excepting for 0. So 0 is working like a gap, like I told you. Here we're gonna have like a space, and a space where this guy can pass, well, sorry, and a space where this guy we have over here in the graph, the alien we said, or whatever we want to call it, can pass freely through there. Okay, can pass, and that way he can freely be in this side, or he can be freely in this other side. Okay, so that's the situation. Okay, so it's so interesting this idea of this space because it will help us to understand better the idea. So what's the domain? Are all the real numbers excepting who? Excepting 0. So what does it mean? It means that there is a restriction for the x values you want to choose. Here, for example, the same happens. There were many restrictions for the x values to choose in here in this exercise. I mean, can I choose any negative number here? Because if you try the square root of any negative number, it will be a math error. Differently than this one, for example, here, do you have any restriction for the x values you want to choose and see if they have an absolute value? No. You can take many absolute values however you want. So here we have this problem. We cannot take 0 because 0 will create that situation which doesn't have an answer yet. So let's see what happened with the range now. Why values are included in the range? So if you see something similar will happen. Now, if we move horizontally, through positive 4 cannot pass, through positive 3 cannot pass, in the 2, in the 1 cannot pass. If we go in the negative 1 cannot pass, if we go in the negative 2 cannot pass. But what happened with the 0? He can pass freely through there, and he can be at this side horizontally or this side horizontally. So this is the point. Okay, this is the point. This is the idea. To understand the y values is better is you have to analyze like horizontally. To understand the x values, the domain, you have to move vertically because they will point to something like that, right? I mean, this is negative 1, and negative 1 has a value over here where it's the head of this alien. So that's my point, okay? So every time you want to assign a correspondence to an x value coordinate, if you see here, you're gonna have to do it vertically, okay? And if you want to see the correspondence value for the y value you have, you will see that this works or this goes horizontally. So this is something that you have to keep in mind. And here, something similar happens like what we have in the domain. So in the range, we have all real numbers except 0. Okay. So again, what was the main idea of all this topic is just keep in mind what is the characteristic of each of the functions, okay? So we will see that and we will conclude with this, the class, today class. So here we have the family of functions we study, and let's start with the polynomial ones. Linear function, f of x equals x. The exponent 1 in the variable x, or just the variable x over there, means you're talking about a linear function. A quadratic function, f of x equals x squared, okay? X squared, so what does it mean? That you will have expressions that behave with that x to the second power, and something similar for the cubic. For the cubic, you will have x to the power of 3. That's going to be like the big difference. What about the other functions we studied? In this case, the absolute value. What's the main characteristic of this one? That you will work with this absolute value bars. Okay, and of course here inside can be a linear expression, can be a quadratic expression, can be a cubic expression, no matter, because it will be inside this absolute value bar. What about square root? Square root, I think you know square root is an expression like this. And again, like we say in the other exercise, of course, just that in second power, it loses the sense to be a square root. But it can be linear, cubic, and any other expression we have study, okay? But why can it be quadratic? Because then you have second power, and the second power and the square root cancel. At the end, this makes something fun, which is at the end work with a linear function. So it doesn't have any sense to work with second power. But the point is, if you have a square root, okay, thinking a square root function. And the last one, which are called a reciprocal function, behaves like this. Okay, so I will show you right now some examples, and you will identify if it's a linear function, if it's quadratic, and something like that's the way you will do that in the homework. Okay, so here is the little activity, and with this we're gonna finish the idea of identify the function. So for example, here the letter A, it's just the match exercise. We'll give you like some seconds to try it your own, okay? I think it's better. We'll give you 10 seconds, but you can conclude this pretty quickly. Okay, to start in order, I'm going with letter A, which if you see has this x to the second power, at the end this becomes to be a quadratic function. So let's see the older one. In this case, we have a square root of x minus 4, so that's why you work with a square root. It's a square root function, simple like that. What about next one? You have the absolute values bars and the x plus 3 inside, so this becomes to be an absolute value function. This one, x plus 1 over x minus 4. I don't know, x plus 1 looks like some linear function, but then I have below x minus 4. So I think this one is a rational algebraic function or a reciprocal function. Reason is has the x on the denominator, and this is more powerful than have an x to the power of 1 on the numerator. So this situation, I have the denominator variable, it's related with this rational function. And finally, I have 5x to the power of 3 plus 2, which will be a cubic function. Simple like that. Okay, something similar. That's like something you will do in the homework, probably a match exercise or an exercise where you have to like complete all the information. Okay, that's all, and I hope that you get it. Please try to practice a little bit more the idea of domain and range. Then I will see with you some weird exercise. Right now is not the moment. If you seen this exercise for now, nobody or there wasn't any linear. So don't worry about it. I think you're clear with how this works. Is the basic one, and it is because it's related with linear equations too. You have been solving passing to the other side and all that. Okay, so something that I need that you review yourself, it's factorization methods, how to simplify rise, because this will be useful for the topic of limits. That's everything for today. Thank you so much and have a nice day.